and register through the link located on the left side navigation bar. Browse the event catalog to schedule a program designed and suited for you and your class. We look forward to connecting you with NASA.
Good morning and welcome to the first Lunabotics Mining Competitions webcast of the year. Thank you so much for joining in, and we look forward to your participation this year. We are very honored today to have NASA physicist Phil Metzger. Dr. Phil Metzger, thank you so much for joining us.
I'm glad to be here.
We are looking forward to your presentation today.
Great. So you asked me to speak today about why we're doing Lunabotics, to give a presentation about the big picture rather than the specifics of the competition this time.
Right.
Great. I enjoy talking about this. This is one of my favorite topics. So we're going to discuss rapidly starting space industry and solar system civilization.
Okay.
So you want to jump right into it?
Good. Go ahead.
Okay, great.
Thanks.
So how do we switch to the charts?
Just arrow. There you go. She'll have to swim. Yeah.
Okay. So what I wanted to talk about is going from a global civilization to a solar system civilization. And a useful way to think about it is the Kardashev scale. Kardashev was a Russian physicist who was looking for signatures of life, radio signals coming from space. And he pointed out to some of the other people working in this field, he wisely noted that we shouldn't assume that a civilization out there in space would necessarily be identical to our own. And so he came up with a scale that of different types of civilizations. And so he defined a type 1 civilization as a civilization that uses the energy of an entire planet. And that would be, he had in mind a civilization much like our own. And so here we have a picture of Earth with lights in the night, showing that we're really used a lot of energy. We're using a lot of energy on a global scale on our planet. Then he defined a type 2 civilization as one that has gone beyond a single planet, and now it's using the energy of an entire star. And then a type 3 civilization has gone beyond a single star, and it's using the energy of an entire galaxy. And people think that's kind of fanciful, but he was just pointing out that you shouldn't think that we're limited to one of these three energy scales. We aren't necessarily bound to just the energy of an entire planet. But today, what I want to do, I'm not interested in talking about signals from outer space. What I want to talk about is what is it like going from one scale of civilization to another? And so I want to ask the question, what about some earlier categories of civilizations? So counting backwards, we've looked at type 3, 2, and type 1. What about type 0 civilization? That would be a civilization that encompasses an entire continent, but it hasn't yet gone across the oceans to span more than one continent. So it's got boundaries. Much like planet Earth has boundaries, we have to leap through space to go to the next place. Civilization also has had to leap across the oceans. Counting further backwards, we might say a type -1 civilization would be one that encompasses an entire river valley. The civilizations on planet Earth really began in 4 river valleys: the Indus River Valley, the Yellow River Valley in China, the Tigris and Euphrates River Valley in the Middle East, in Mesopotamia, and the Nile River Valley in Egypt. And the reason civilization started in these river valleys was because the silt from the flooding of those rivers provided a great place to learn how to do agriculture. And they discovered that by using human and animal labor to do irrigation and cultivating in the fields, they could grow vast quantities of food, which is an energy source, in a small area. So they could support a much larger population in one area than they ever could before. And that allowed the development of cities. And that's what the word civilization means. It means living in cities. So the ability to live in cities and have civilization came about from discovering an energy source that was specific to river valleys. Once they had figured this out, they were able to expand their civilizations within those river valleys to fill up all the area. But they really couldn't leap from river valley out across the deserts and across the mountains to fill up the rest of the continents until they had developed an infrastructure of roads and towns with armies protecting those towns. Like if you leap forward in time to the Roman Empire, for example, they were famous for the Roman roads, and they had their forts throughout the empire and the ability to move resources around. And there was a lot of transporting of grain from Egypt across the Mediterranean on ships, barges. So they had developed the infrastructure to leap beyond the river valleys and support a continent-size civilization. And then moving further back, we might say a type -2 civilization. It's not really a civilization at all. That would be humans living in isolated enclaves, maybe a fort on the top of a hill, where people lived doing hunting and gathering and not a lot of agriculture because they hadn't yet discovered how to do it. And this was before the time of cities. Now, what I want to point out is that every time you go from one of these types to the next type, there was a barrier that had to be crossed. They had to figure out how to go to the next level of energy, the next level of organization, of social structures, and of logistics, transporting resources, in order to expand to the next level. And so that's what we're talking about today. We're talking about how we're currently a type 1 civilization. How do we leap across the barriers, the energy barriers, the barriers of space, in order to take civilization to another level, an entirely higher level, different and bigger than what we've seen so far? So I want to make a few predictions. We are essentially type 1 right now. If you want to be really specific, people have said, well, Carl Sagan defined a logarithmic scale, and he said that we're a 0.7 type civilization on that. But we're essentially type 1 in the sense that Kardashev meant. We're probably not going to get much more developed than we are right now, because we've been developing our civilization based on non-renewable resources, and they're going to run out. They have to, because they're non-renewable and they're a limited quantity. So when we've developed to this point, this size of a civilization based on non-renewable, limited resources, we've pretty much hit the limits of the planet. If we can transition to non-renewable resources, we could continue growing. But I'm predicting that and a lot of people are predicting that we're in a race here, because we've got to get beyond the non-renewable resources before they run out. So I think we've got a choice. We can either go on towards type 2 and achieve it within the next 50 or at the most 100 years, or we might never get there at all. Because if we run out of the non-renewable resources, if we fail to take civilization to the next level, people who talk about sustainability say our planet can't sustain the current levels of population, and we would have to move backwards, which would be really tragic. On the other hand, if we do move forward and achieve type 2 within the next 50 to 100 years, I think moving on towards type 3 would really be easy. The next barrier from type 2 to type 3 seems insurmountable, having an interstellar civilization. But as I'll show you, once you've got type 2, the increase in the capacity of civilization is so huge that moving on interstellar is really not that big of a step. So talking about this barrier that we're facing right now, going from type 1 towards type 2, as I mentioned, we're using a lot of non-renewable resources. People have been predicting how long do we have before the amount of energy we're using begins to run out. We may have just recently got a reprieve with fracking. I know fracking is controversial because of the implications for the environment. But even if we do fracking full scale, they're saying it's 100 years worth of energy, but that's at current rates of use, not taking into account the fact that China's still got the ability to grow 4 times their energy use before they reach the per capita level of the West. And other parts of the globe are still growing their population and want to industrialize too. So we really need 10 times the current energy levels if the whole world industrializes and reaches the predicted population levels. And so taking that into account, at most fracking could give us 30 years of a reprieve before we hit the barrier. So we're trying to advance renewable energy sources. And through the midst of all this, people are realizing that it's a global issue. And I was really struck by this when I went to deposit some clothes in a clothing box, and I noticed that it didn't say Goodwill on the box. It said Planet Aid. I thought it was kind of funny that putting shoes or socks in a box could be considered saving the planet, but it really illustrates the fact that the people have become conscious of the fact that what we're dealing with is a planet-wide limitation. It's a barrier. We're nearing the limits of a type 1 civilization, and that's fundamentally what's going on right now. All the global challenges we're facing are all focused on the fact that we are coming up on the next civilization barrier, and we've either got to back up from that barrier or we've got to leap over it. It's a choice we've got to make. So the message I want to give today is let's not be limited by that planet barrier. We can realize that we really don't have a resource problem. The only thing we've got is an imagination problem. We live in a solar system that's unbelievably wealthy. We've got 1 billion times more of everything in the solar system compared to what we have on Earth. There's 2 billion times more energy leaving the sun than what falls on the Earth. There's 1 billion times more high-grade metal and ore in the asteroid belt compared to all the high-grade ore in the crust of the Earth. 2 billion times. There's billions of times more of all the volatiles in the outer solar system than what we have on Earth. For example, Charon, the moon of Pluto, is made, we believe, in bulk composition of, I think it was methane and ammonia. I can't remember for sure, but I know there's perhaps upward of 50% of its bulk composition is methane. So there's really no shortage of any resource in the solar system compared to the scale of civilization we have right now. And so when I say it's an imagination problem, let's take a look at the way people think about these problems. We hear people saying that we need to think globally but act locally. Well, that's good, but it kind of points out how we've limited our thinking, because the global nature of our civilization isn't really the solution, it's the problem. This statement here is telling us think globally because it's a global problem. But what I want to say is thinking globally is the new way of thinking too small. Let's not think just globally. Let's think beyond the problem. The problem is the solution is beyond the globe. Another thing people say is let's think outside the box, and that's good, but the problem isn't a box. The problem is that we're limited to a sphere, the sphere of the planet Earth. We've moved across the surface of the planet, this two-dimensional surface, and it's a curved surface. It curves so that it closes on itself, and therefore it has finite area, and we've already filled it out. And so there's only one other dimension we can move in, and that's perpendicularly off of that surface, which means moving outside the sphere, outward into space. A lot of people have a hard time imagining what that can be like. They think it's impossible. It's too hard to do it. And so this is where the imagination problem comes from. What they need to realize is that we shouldn't limit ourselves to the type of civilization we have right now. You can imagine something greater than that. Imagine what it was like for the Polynesians at the time that European ships first came. The Polynesians had developed remarkable abilities to cross the ocean, and some people actually crossed thousands of miles from Tahiti to Hawaii 2 or 3 times in their life. But it was considered an epic and heroic journey to do so. The reason why it was so hard was because they had no metals, living on volcanic islands where the only rocks were igneous. They didn't have any high-grade ore, and so they couldn't find any metals to refine, and there was no metallurgy in their civilization. When Europeans showed up with ships that relied on, it was built by industries that were based on metallurgy and the the growth of industry along that pathway, they were shocked by the scale of civilization that confronted them. Imagine how much more of a leap it's been since then. We now have ships that cross the ocean with essentially entire cities contained on those ships. We have container ships taking things back and forth across the ocean. If you own a cell phone, a mobile phone, the materials in that phone have crossed the ocean at least 4 times in the manufacture of the phone. The metals came from Africa. They were probably refined somewhere else, maybe in Japan, maybe in the United States or somewhere. The plastics came from petroleum products and perhaps in Saudi Arabia. They were refined somewhere else, perhaps. Silicon chips were made maybe in Silicon Valley or maybe in China or somewhere. All the parts were assembled in some country, perhaps China, and then it was shipped across the ocean again and sold as a consumer product on another continent. The concept of doing that would have been unbelievable to the Polynesians, but yet here we are doing it. And so what can we do in the future that we currently have a hard time believing? I want to show you what I think we can do within the next 50 to 100 years, really within the next 20 years. Now, this has been talked about for decades. And back in the 70s through the 90s, there was Gerard K. O'Neill was leading the effort. And this is an example, a concept picture of a orbiting manufacturing plant that O'Neill was talking and his colleagues were talking about. And in their studies, they predicted that you need to have 10,000 people living in one of these orbiting platforms before it would become self-sustaining and make a profit. And because it would have taken a facility large enough to house 10,000 people, it was really too expensive. And there was no way that Congress or the parliament of any nation was going to pay for this sort of a gigantic space activity. It's unfortunate. It would have been great to do, but it was really beyond the economies of Earth. This is what it would have looked like inside one of these orbiting colonies in space, a gigantic cylinder rotating to create artificial gravity with thousands of people living there, working at jobs, creating power stations that would beam solar energy down to Earth to make a profit to sustain their world up there in space. An advancement over this concept came in the 1980s. There was a summer study done at the NASA Ames Research Center looking into the concept of self-replicating lunar factories. And this would be a robotic factory. So you wouldn't need to have 10,000 people living there. And in their study, the idea was that you'd have one factory that was self-sustaining, and it would build 3 copies of itself, and those would build 3 more copies, and those each would build 3 more copies. And pretty soon you would have millions to billions of times the industrial capacity of planet Earth. Well, that's a great idea, and it's a way to get to this large in-space capacity from a more humble starting point. But even with this more humble starting point, they showed that it would take probably 100 tons of hardware. And here's a picture of a lunar factory, a self-sustaining lunar factory as they envisioned it. This was estimated to be 100 tons of hardware that had to be developed and then launched from Earth before it would become almost self-sustaining. And in this concept, they were still manufacturing the computer chips on Earth and launching them from Earth. And remember, back in those days, making computer chips required much larger machines than what it takes now. So that's why they didn't have full closure on their industry. They still would require a lot of launching stuff from Earth to sustain it. Well, since then, we've had some game changers. And so what I'm going to present to you is based on the new vision that has developed over the last several decades since the 1980s. One of these game changers has been the tremendous advancements in robotics. And that's what the Lunabotics competition is all about. The robots that we have nowadays, by the way, this is a picture of Lunabot, which was a joint product of NASA and General Motors Corporation. And robotics has been making tremendous advances. We now have robots that can identify objects that they've never seen before based on their similarity to other objects that they have seen. And they can identify objects functionally. And this is what Hans Marovec at Carnegie Mellon would have called lizard-like artificial intelligence. the increasing levels of artificial intelligence that we need require greater computing powers. And there's been another revolution going on in the last 3 decades, and that's computing power. So these were just some computer speeds that I pulled from a Wikipedia article, and I plotted them showing the millions of instructions per second versus the year, and plotted it on a semi-log plot. And you can see that it's growing exponentially. And and computer experts say there's no end in sight yet, although we might have maxed out the number of transistors we can fit on a silicon chip. That's the geometric growth of that is known as Moore's law. Nevertheless, we can begin sandwiching the chips, we can parallelize, and so the growth of computing power is nowhere near the limit yet. And so the predictions are that we really are going to reach the levels of computing power needed for not just lizard scale artificial intelligence, but what Maravec called monkey scale, and then even human scale, where you've got monkey scale would be where the computer maintains a model of the world and it's comparing what it sees with what it understands the world should be. And human scale would be the ability to generalize. So you learn something, the robot learns something, and then it generalizes and applies that to other cases. It doesn't mean that you've got a robot that's like a human in all ways, but it's a definition of a type of artificial intelligence. And the predictions are we're going to be there in 40, 50 years from now, having human-type artificial intelligence. Another revolution that's going on is digital manufacturing, or what's popularly known as 3D printing. So here we've got a picture of a 3D printer and a part that it's made. And here are some more pictures of things that have been made in 3D printing. You can even make things in 3D printing that can't be made by any other means, and that opens up the door for new technologies. The lower right corner is a picture of 3D printing of an entire house. This came from the University of Southern California, from Contour Crafting. One of our collaborators, Boris Kosnevich, who is developing 3D printing on a gigantic scale. And another thing that's a game changer for lunar industry is the discovery of ice on the moon. It used to be said that the 3 elements you could not get very readily on the moon were hydrogen, carbon, and nitrogen. But with the L-Cross mission crashing into a crater on the moon and splashing up the volatiles from that crater, we now see that there are vast quantities of water and also carbon and nitrogen compounds. They say that there's enough ice on the moon that if you converted it into liquid hydrogen and liquid oxygen, you could launch one space shuttle every day for 1,000 years. That's how much ice we've got on the moon. And this is a game changer. As one of my colleagues, Dr. Tony Muscatello, said, now there is nothing that can't be made on the moon. So that's game changing. And one other thing I want to mention is during the past decade, during the Constellation program in NASA, we've been developing these technologies. And here we've got a picture of a field test on Mauna Kea where we had excavators delivering soil into chemistry plants, which extracted oxygen from the soil. And we've used solar concentrators that one small business made, a regolith conveyance system made by another small business, a chemical processor made by another one. And the oxygen that was produced from the soil was then used to fire a rocket thruster. So it went from dust, volcanic dust, to rocket thrust. And the test was called dust to thrust. And here's a picture of some of my colleagues testing these technologies in a reduced gravity aircraft, showing that in lunar gravity, these technologies work and function. And so this leads us to a new approach to lunar industry. I want to just rush right into this for the sake of time. How much time do we have, Susan?
We still have 37 minutes.
37 minutes. Okay, so I want to make sure I don't get lost in the details. The key ideas are, first of all, we're not going to launch everything from Earth. We don't have to build a complete lunar factory on Earth and then launch it from the Earth. Instead, let's spiral up to that. We can launch simpler things and build most of the parts for the next device and then send the missing pieces from Earth and put them together on the moon. And by doing it this way, we can build the majority of the mass on the moon and spiral upwards. Also, we want to use appropriate technology at every step. We don't have to have fully high-tech, fully developed equipment such as you would need in a self-sustaining factory. From the very beginning, you can build simpler things that are low-tech but easy to make in space, and they will contribute much of the mass for the next generation of hardware. And then we don't have to develop all these technologies for space. They're already being developed for terrestrial needs, and we're just going to spin in what's already being developed. And last of all, I want to point that technology is advancing exponentially. So we don't have to base our plans on what's currently available today. We can reasonably anticipate that technologies are going to be available in the near future that aren't quite yet ready. For appropriate technology, here's a picture of what people were living in America in 1620 compared to what people were living in Europe in 1620. The people in Europe didn't put entire buildings on ships to go across the ocean. They went across the ocean and they built houses after they got there using materials that were available in America. But because there was not the same level of industry available in America, the level of technology had to be lower. And this is what we call appropriate technology. You use technologies that can be supported by the industry in the environment where you are. Another example of appropriate technology, people found that if you ship a water pump to a place where the local industry can't yet sustain those materials and those parts, then they would rapidly break and they would not be used. So you start out with maybe foot-powered water pumps. Eventually you graduate to pedal-powered. Eventually you have engine-powered. And eventually you have large-scale water pumps. But at every step of the way, you develop the entire industry in the local area so that it can be sustained using local materials and local processes. This is what we need to do in space. So we came up with a chart of several generations of lunar industry, going from generation 1 up through generation 6 and then generation X.0, which is the long-term looking at the solar system. And there's a lot of details on this chart. We probably don't have time to go through all the details, but I just want to point out that the first column numbers the generations. The second column shows how humans would interact with the robots. So teleoperated is what most people in Lunabotics are doing right now. We're challenging the Lunabotics competitors to move towards autonomy, because in lunar industry, it will need to move towards autonomy, because by the time you move the industry to the asteroid belt with the large communication time delays, you really can't do teleoperation anymore. So we need to move towards autonomy. The industry goes from simple scale, small scale, up to large scale by the time it reaches generation 6. The early industry would only make gases, water, crude alloys, ceramics, and solar cells. But by the time of generation 6.0, the industry could make everything that could be made on Earth. And you start out by shipping the electronics from Earth, but eventually you start making the electronics, even the integrated circuits, on the moon. I'll skip the next couple of charts for the sake of time, but let me say, here's a chart I want to show. We've done modeling of lunar industry. We base the modeling on actual hardware that we've already developed and on studies that other people have done. And it's a iterative model that explores the key parameters of lunar industry and tries to investigate how much mass do you need to launch, how much can you make on the moon per year, how fast can you work your way through these advancing generations of industry. And it explores some of the key parameters, and it's not definitive, but our study was intended to develop more interest, to get more people studying this. And so here's one of the predictions of space industry from our model. We've through these 6 generations, the blue curve is the baseline. This is the mass of hardware in tons that you need to send to the moon in 2-year intervals. And it adds up to about 42 tons on the blue curve. The red curve is if you don't make any electronics at all. And you can see that the amount of electronics you have to send to the moon as the industry grows becomes exorbitant. And so we wanted to avoid that. And that's why we have to make electronics on the moon. The gold color, or is that green? I'm colorblind.
It's green.
It's a green color, okay. The green color is if you make all the electronics except the computer chips. And beginning from 6.0, even that begins to grow exorbitantly as the industry expands exponentially. So even the computer chips need to be made in space. And so, but there's no reason why we can't do that. We can, if you can build the metals and build the electronics, you can assemble a stereolithography machine using robotics the kind of robotics we're going to have 20 to 30 years from now. Those assembly tasks are going to be possible. So there's no reason why you couldn't assemble stereolithography machines on the moon, where you've made most of the materials on the moon, sent the computer chips for those machines from Earth, set the advanced components, and then you begin manufacturing the advanced components on the moon later on. Here's another prediction from our model. We were very conservative and we put more energy into building solar cells than was really necessary. And so the modeling is predicting that you'll have 30 times more power than you'll need throughout all 6 generations of lunar industry. So you're able to generate vastly more solar power than you need and still achieve all the other objectives of the industry. And the model predicts that the industry will grow exponentially. So the blue curve pointing to the left shows the mass of hardware that you've accumulated on the moon. This includes what you've built on the moon and also what you've launched. And you can see that the 42 tons that you launch is negligible compared to the tens of thousands of tons of hardware that are accumulated, mostly through manufacturing on the moon. The number of robots that you build, originally they're being sent from Earth. Then you start building the majority of the mass on the moon and sending the electronics from Earth and having the robots assemble the further robots. And eventually, at the very end, you transition to building the entire robots on the moon. But by the end of this process, it's predicted that you'd have 100,000 robots on the moon. And this is using conservative and reasonable assumptions in our modeling. So this is within just 6 generations of industry at 2-year intervals. This is 12 years from now. This could be possible if we supported it at the full speed. The biggest challenge is printing speed. 3D printers are currently putting out about 0.1 to 0.15 kilograms per hour. Those would be the middle curves. And so these are the number of years that it would take to reproduce one set of hardware. And this is for different numbers of printers contained in one set of hardware. I don't want to go through all the details for the sake of time, but most experts believe that 3D printers are going to achieve 1 kilogram per hour output, which means that we can get the time to reproduce one set of lunar hardware down to a year or less. But you don't have to use just 3D printing. We could also use casting and for the majority of the mass. And so it's very reasonable that we can do this using manufacturing techniques that are available now or in the very near future. The modeling shows that we can do, if you have just 0.4 kilograms per hour output from your printers, you can go through all 6 generations of lunar industry in less than 20 years. And the number of robots you would have would be in the tens to hundreds of thousands in just 20 years from now. The quantity of hardware you have on the moon is a function of where you're located on the moon. If you're at an equatorial location, you only get about 40% of the month to do your industry, because then you're in darkness or the sun's too low to the horizon for the remainder of the month. But if you're near the poles, you get about 70% of the lunation to do industry. And this chart here shows that you get about an order of magnitude faster growth in your industry if you're near the poles than if you're near the equator. And finally, the most important graph is how much mass do you have to launch to the moon? Well, with the baseline strategy I already mentioned, it's 42 tons of hardware to the moon. But if you take a reduced approach and we don't grow the industry exponentially, we just reproduce the minimum amount of hardware in every generation, we can get the launch mass down to as low as 12 tons of hardware. And at the end of 6 generations, the modeling in the lower graph predicts that you would have about 150 tons of hardware on the moon. This greatly agrees with the study done by NASA Ames. They were predicting about 100 tons of hardware on the moon to reach the point of being self-sustaining. We're almost self-sustaining. We're saying about 150 tons and you're fully self-sustaining. And furthermore, you only had to launch 12 of those tons. And it was spread out over 20 years. So you didn't have to pay for it all up front. Furthermore, by doing it this way, by developing it incrementally on the moon, you're developing it in the environment where it has to operate. It allows you to start immediately with existing levels of technology. It allows us to develop it in the right environment. It allows us to pay for it incrementally as we go. And it allows us to reduce the launch mass from 150 tons down to 12 tons. So I think this is the way to do it. Start right away doing what we can do on the moon, building what we can, launching what we need to, and spiraling upward as we go. I think this is the right approach. And it's something we can do beginning right now. And within just 20 years, we could have a fully self-sustaining industry. After Generation 6, what do we do next? Well, we move the industry to the asteroid belt. And so the modeling actually accounted for this. The modeling included setting aside the resources to build a fleet of 6 spacecraft taking of 20 tons each, taking 12 tons of payload each, including all the propellants. The modeling includes the manufacture of all the propellants to send them to the asteroid belt. So then you can begin this industry on the asteroid belt where it can really expand, where the real benefits come. And after 20 more years in the asteroid belt, this modeling predicts that the industry would have 1 million times the industrial capacity of the entire United States. And after just 10 more years, it would have 1 billion times the capacity of the entire United States. Not to say that you would necessarily want to do that, but you could. And so the question is, what could humanity do with so much capability? And maybe you should ask, really, what could you not do with 1 billion times our current capacity to produce goods and services, 1 billion times the capacity to modify the environment of space, to terraform planets, to create environments to live in, to bring resources back to Earth? It's hard to imagine what a civilization like that would be. That would be a Type 2 civilization. And according to the model, you could get there 20 years, you're self-sustaining, 20 more years, you've got 1 million times Earth's capacity, and 10 more after that. So a total of 50 years, you're a fully Type 2 civilization. So here are some scenarios of what you could do once you start to achieve a Type 2 civilization. The first one we've called the global relief effort. And the idea is bringing the resources back to Earth. So you could build power stations and beam all the energy you want. So you can convert to totally clean, totally green energy.